Students, so now in this video we'll see about the remaining PLL performance factors there. So in the previous video we had seen about the loop gain and the track range or the lock range there. Now we'll see about the capture range. The capture range is nothing but the maximum range of frequency when the PLL is going to attain lock, within which your PLL is going to attain lock is going to be called as the capture range, or the other name for capture range is your acquisition range. So suppose if there is no input that is going to be applied to your phase detector, then in that case your VCO is going to operate at a free running frequency. If the input frequency is going to be equivalent to the maximum tracking frequency, then we say that the phase lock is going to occur. So here in this case, for tracking range, the error voltage must be maximum. That is, when it is going to move the VCO frequency from the frequency free running frequency to your maximum tracking frequency there. So here we say that the error voltage is nothing but the average output voltage from the phase detector, and it is proportional to the average phase difference between the input and the output feedback waveforms there. So here we say that the maximum input frequency at which your phase lock occurs is going to be termed as the maximum capture range, and when the phase difference between the Vi and the V0 is going to be constant changing there. That means that we say that when the input frequency is going to be phase locked with the oscillator frequency, the maximum phase difference between the input frequency and the oscillator frequency should be 90 degrees, and it should be a constant one there. The capture range is going to be given by your FCR is equal to plus or minus AL into del phi. So here in this case we say that the phase lock will not occur when the input frequency is going to be equivalent to the minimum tracking frequency there. So here we are going to define the maximum and minimum of the capture range. So the maximum capture range is going to be your free running frequency plus the capture range frequency there. And FC minimum, that is the minimum capture range is going to be your free running frequency minus your capture range frequency there. So we say that always your capture range is going to be less than the tracking range there, because your average input voltage is going to be less than the amplifier voltage maximum. That is when both input and the output is not going to be phase locked. So next is we are going to see about frequency synthesis. So frequency synthesis, the other name for frequency synthesis is your frequency multiplication. So here in this case what we are going to do is, in your basic PLL PLL block diagram, the feedback, the output from the oscillator is going to be given to a frequency divider network. So the output of this frequency divider will be given as input to the phase detector there. So when I am going to give it, we can see that your F0 by N, the output of the voltage, here we can see the output of this voltage control oscillator is going to be F0. So when this F0 is going to be given as input to this frequency divider, where it is nothing but 1 by N. So the output of the frequency divider will be F0 by N. So the input to the phase detector will be your F in from the crystal oscillator. So when we say that the phase detector is going to be, that is this PLL is under lock condition, is when F in is equal to F0 by N. That means that your F0 is equal to N times your F in. So automatically we say that the output frequency is nothing but it is going to be multiplied by a constant, and the input frequency is going to be multiplied by a constant there. So here when it is going to be multiplied by a constant value, the output frequency is going to be higher than the input frequency. So we say that this circuit is going to behave like a frequency synthesizer or a frequency multiplication circuit. So here, as the input frequency is going to be multiplied by a selected factor, it is going to produce the desired higher output frequency there. So in that case, we say that the oscillators are going to be designed to generate a stable frequency there, where it cannot be directly adjusted. So your oscillator frequencies can be accurately divided by a digital counting circuit there. So here this process we are going to use it in your PLL system to multiply the input frequency there. So here we are going to use a frequency divider is going to be included in the feedback path between the output and the output of your VCO and the input of your phase detector. We are going to use a frequency divider block. The output frequency f0 is divided by a selected factor n, and the action of the PLL loop causes the divider output frequency f0 equals the reference input frequency fr. So the output frequency f0 is equivalent to n into fr. So to get this frequency, what this n value, what we are going to do is the frequencies divider can be used constructed using a cascade of n flip-flops, where this n flip-flops can be used to divide by frequency by 2 power n. So if I am going to use 4 flip-flops, that means that frequency is going to be divided by 2 power 4, that is 16. If I use 5 flip-flops, that means that the frequency is going to be divided by 2 power 5, it is 32. So here if I don't want the standard value 16, 32, 8, if I want an intermediate values, then I can construct that using, suppose if I am going to use a 4 flip-flop cascade flip-flops, in that case counter, the counter I can design it to count for a value of 10. Once 10 is reached, I can reset to 0 condition there. So here your frequency dividers can be constructed with the switches. So here in this case, by selecting any required division. So according to whichever division of value frequency I want, that can be set with the help of the switches there. So suppose if I am going to use a programmable frequency PLL is going to be used in the PLL system, the system output frequency can be adjusted according to our requirement there. So this is your input signal frequency. This is going to be the output of your oscillator, which is going to be divided by a divider value n. So here in this case, these two signals are going to have a phase difference there. And now your f0 is nothing but this should be equal, so n into fr. So I am going to get, for one time period, I am going to get so many pulses there. So that means that if the width of the pulse is going to be less, then automatically the frequency is going to be high. So we say that the frequency of the output signal is going to be high compared to that of the input signal, and it is going to be multiplied by a factor n. These are the performance parameters of your PLL system. Thank you.